Hello, my name is Herrera,
I'm Ben Grau.
I'm Dylan Hurley.
and we chose to solve the supercharger testing cell titled Which Drive Belt? The goal of this project is to give us, undergraduate engineering students, an idea of what a real-world engineering problem might be like. Most real-world engineering problems are ill-structured and require the engineers to utilize their vast skill sets in order to solve them. Problem statement. A supercharger testing cell is suspected to be functioning improperly due to a problem with the drive belt. Test engineers hypothesize that the tension in the belt is too high for the belt that is currently being used. So, we need to find the optimal running tension for the belt, which is going to be under 490 newtons or 110.16 pounds, the factor of safety for our belt and tension setting, and the lifespan of the belt as well as cost and availability.
Our methods for determining the proper belt to use consisted of drawing the supercharger pulley system in AutoCAD, using the AutoCAD list command to determine the effective length of the belt, using the Gates belt tension calculator to determine the maximum amount of ribs the belt can have if the maximum allowable force is 490 newtons. Using the effective length calculated in step 2 and the maximum amount of ribs calculated in step 3, we narrowed down the Gates belt options that meet these constraints. We analyzed the features of the belts that meet these constraints and chose the belt that would be most ideal for the system while taking into account cost and availability. Once we have chosen a belt, we calculated the ideal tension of the belt and determined the factor of safety. Then we found the service life of the individual belt.
Because we didn't have a physical model of the supercharger testing cell, we modeled it in AutoCAD exactly as shown in the problem statement. We then took the perimeter of the testing cell and broke it into different sections and measured the length using the list command. Then we summed the lengths of each section, which came out to be 2,233.6 millimeters, or 2.23 meters.
At this point in our analysis, we made the realization that both sides of the belt will be in contact with the pulley at any given point in time. Therefore, we decided to choose a belt that was double-sided, aka had ribs on both sides of the belt.
In order to satisfy our length constraint, our rib constraint, and our double-sided belt constraint, we used a 6-ribbed double-sided belt to satisfy our problem. In order to find out the tension, we used an industry standard equation listed here.
To find the ideal tension, we first found the horsepower of the engine. The engine produces 70 kilowatts, which is equivalent to 93.9 horsepower. In order to use the industry standard equation, we had to multiply this horsepower by 1.15 to get design horsepower. This left us with 107.95 design power. After plugging in the values, we found that the ideal tension for our double-sided Gates belt is 103.79 pounds. In conclusion, we decided to go with the Gates DK060867 serpentine belt. The optimal tension for this belt will be 103.79 pounds. The factor of safety with regards to the pulley being able to tension this to the proper tension is 1.061. The service life of this belt is expected to be 50,000 miles based on customer usage. Pen and paper calculations can only get you so far in a real-life engineering problem. In order to find an accurate solution, you must get hands-on with the problem and run several trial and error tests. These tests should be constrained by the prior calculations you make in order to narrow down the solutions as much as possible. Engineering is a profession of trial and error, but the real expertise lies in how much error you can eliminate before attempting any experiment or solution that will cost time and money.
When working in teams, you always find that each team member will have a preconceived idea of how to solve the problem. Effective teams learn to take each element of each individual approach and formulate a method of solving the problem that could only be achieved through collaboration.
Our recommendations to the next team attempting to solve this problem: ask as many questions as possible to help you constrain the problem, and try to visit the manufacturer so that you get a better idea of how the testing cell works.